Good day to you. This is Anagalactic bringing you the next in our series of 10-minute presentations in Imaginarity, which is a mathematical term with a geometric interpretation. Imaginarity is now famous in the complex number system. Where we're at now in this series is we're transferring to space-time geometry, a 4D linear system which composes pseudo-hyperbolic space, quite baffling in the geometric sense and enormously baffling in the mathematical sense. In the space-time system, light does not propagate as a sphere. Not in the geometry it doesn't. A lot of physicists who are just starry-eyed about space-time, and then every time they say light cone, their eyes light up like little tots at Christmas time. But it's sad because light does not propagate as a cone. And in fact, the only reason that it looks like a cone, well, in one sense, the reason why it looks like a cone is because it's a projection down from 4D, which cannot be visualized, to 3D. So you have to stretch your imagination because that cone, every slice of it that would be a circle, right? Every slice of it that would be a circle is actually a sphere. So it really represents a propagating sphere. And so the light cone is light speed. It is really the path of a photon. If you took the center of the cone, where time is going forward, going up, and it just is a reflection going down. The light cone comes in, representing light as it's converging on your position. But if you're a photon, you go out on that cone. You're nowhere in, well, you can't say nowhere inside because you're nowhere inside the geometric cone except on that circle, any slice, but that's actually the expanding sphere of the photon. And this is the quantum paradox in the photonic sense, that the photon, which you are at that point, because that point on the cone is zero, and that's where the photon goes. So if you're that photon at that moment of time, and you start action, you expand as a sphere, upward. So each circle is actually the sphere. And that is the spheric part of the light cone. You don't see it, but it is actually a spherical shell expanding upward. Which I would have to say is just a little bit hard to visualize, but I hope that helps. That cone is not a cone. It's a certain type of projection down from 4D, where that cone is not a cone, it's an expanding sphere of light. And so that would be the edge, basically, of reality. It's everything inside that cone is room for maneuvering in space, but not outside the cone. So that's another baffling thing about the light cone, is that none of the graph is real except what's inside the cone, because outside of it is undefined. Now, inside of it, you don't use spheric geometry, you use hyperbolic geometry, which I just want to make simple for you, so if you're baffled by that, or you would be quite normal to be baffled by that, even if you know what hyperbolicity is, or hyperbolic anything. It's an inside-out sphere. It's inside out. That would have to be elaborated, but that's not my purpose in these very short lectures, and we've come 7 3/4 minutes. So what I would like to tell you today is how we can transfer the pseudo-hyperbolic space-time system to an actual sphere, so that the geometry is spherical, not hyperbolic in linear space. It is linear. That's why we have all the calculus in there. Very, very daunting, and it's virtually impossible for a human to do it. Einstein knew how to do it somehow, but now we just let supercomputers do it. And space-time computation is extraordinarily important. For instance, in astrogation, which I found out is actually a word, space navigation within the solar system, you do have to account for relativity for the obvious reason that it takes time for light to travel. This would be like the radio signals to your craft or collecting data from your telescope or craft. Well, it's far enough away that there is a time differential, measured as time lag. So the necessity for space-time geometry is intuitively crystal clear, and I hope you see it crystal clearly, that with volume space, you now must take into account the time lag. For instance, from the center to the edge, there is going to be a time lag that's not really noticeable in Earth computations, because the time lag is virtually nothing. Not so in cosmic space. It becomes quite significant. The spheric formulation is so simple that I want to just give that to you now and close off this lecture. In the next lecture following this, we'll explore spheric geometry more intently. I've done so in my 350 some lectures before this. I've been discovering this on my own, so this has been a work in progress. But the summation of the whole thing in terms of current physical mathematics and physical geometry, we do have space-time, which is the correct linear solution. But it is linear, and that's actually a big problem. And we'll be right back. This is Anagalactic, bringing you the secrets of the universe. Stay tuned for our next lecture, and keep